Okay, so I'm going to introduce simplicial homology and Rham's cohomology. So homology and like completely topological homology, and then cohomology of that is just a. So I don't know the cohomology well, so I would just go directly into some Rm and then subsets of Rn, and then for that cohomology is just a dual group or something like that. So that's why it will be simple. Okay, so we have the fundamental group, first fundamental group of topological space with a specific base point, which uses homotopy to define groups which are topologically invariant and functorial. Now, what we want is the cohomology, the homology groups, which uses sort of triangles and boundary operators to measure the same object, same topological invariance of holes. So what we form is this: define the delta n to be the standard k simplex, or um, the standard n simplex in Rn plus 1. So it will be just the you take TI where the indices go from 0 to n minus 1, where these are elements of Rn plus 1, such that sum of Ti is equal to 1, and Ti, each of them goes from 0 to 1. Should be checking out all of this. Okay, so we have a topological space, and what we're doing is using this triangle, n-dimensional triangle in Rn plus 1, and we are mapping this into here using a map which is just continuous. So if we want to map triangles, we should be making it injective, and so that it doesn't have intersections or something. We can do that. That gives you a homology, but it's not required. The homology which will be produced by just a continuous map is exactly the same. The groups will be isomorphic, so we don't need it. So this is the simplicial homology, and that's good enough. And this is a brief overview. So what we are doing is taking the triangle here and mapping it to somewhere like here. In n equals to 3, this would just be everything that is inside this. This would be a tetrahedral. In R2, it would be the line. So what we're doing is just mapping these delta n's inside the space X, and that we are calling n simplex inside the topological space X. Now what we are doing is we want to work with these sigmas. So we have the set of all sigmas, but that's not enough. What we need is this set Cn. So by sigma I mean it is just a map to X which is continuous, and I have from n belongs to natural numbers. I can do 0, right? I'm pretty sure. I'm thinking we should be able to do the 0, or it doesn't really matter. That should be the empty set or something like that. What do we want the Cn to be? And Cn must be a group. So we have the sigma n's, which are like for fixed n, it will be like a very large number of maps, like an infinite dimensional vector space, just a continuous map from this space to this space. Not even a vector space, it's just a space which is weird and shit. what we want is to have a abelian group whose generators are the sigma n's. So we want the sigmas to generate a Cn group. Sigma from delta n to x, which is just continuous. Right. So a generic element here would be something like generated by integers, by the way, generated by integers or real numbers or whatever we can have any ring we want. So our genetic element look like this: ni sigma I, where ni belongs to integers. Let's say we are not doing the real numbers, let's say, for now. And the group operation is just add them together and give you a different element. So it would be just take random ni sigma I and another random combination of ni dash sigma I, and it would just add them together because we have the addition of integers. So these sigmas are just the bases, sort of the generators of the group. And then now what we have is all these CNs. So we have a C, I'm pretty sure we have a C0, we have a CNX, CN, we don't have anything in the between right now. So what we have is, let's write it like this. We have all these abelian groups. Now what we want is to define, so what we're doing is we're asking the question, so these are n-dimensional triangles, these CNs. These CNs contain the groups generated by the n-dimensional triangles in our specs X. We want to ask the question, if an object is boundary of something else, so let's say a football will be a boundary of some other shape, and whose boundary is 0. The boundary of a football is 0, and its boundary of something else, that is something whose boundary is the sphere. And that is sort of the question we are trying to ask. We are using this boundary operation. So now we define the boundary operation from which would be from Cn x to Cn minus 1x, which is just use the kind of orientation and triangles to define the boundary. We can take a sigma. What we are doing is we have a Cn which is generated by the sigmas. Now we are defining a kind of map on the generators and asking that it would be linear map. So if we define it on our generators, then we can define a whole map on the whole group, and it's defined like this: minus 1 to the power I sigma restricted. So we remove one of the edges here. Now I'm not explaining this very nicely, but the whole point is if we have a triangle like this and a triangle like this, the shape forming by them should be the whole thing, not just the two parts of a triangle. So the boundary of this object is this guy, not the middle part. So this should cut each other off. So that's why we should have a sign orientation, and that's why this guy takes care of that. So what we essentially defined here, which I have not defined properly, but we have here is a sigma delta n map, n plus 1 delta n for each of the n's. There are n's here, there are n's here. And now what we need to check is this condition, that I compose delta twice. So delta n plus 1 composed with delta n. I go here and then here. Boundary of a boundary is 0. There is, because of the sign convention, because of the minus side to the right, we can check this works out. So this gives us what is called a chain complex. Chain complex is like a chain of sequence of abelian groups or vector spaces with a map, so that I think the map should be something like a subjective or something. No, it doesn't need to be subjective. Of course, not. So the map should be like, composing the map for the two of them should be 0. So the map looks like this. It maps this object to some smaller neighborhood, and then composing it again with the map next time goes to 0. And then this maps to, so this is 0 and this maps to the kernel. So this is what the structure looks like. This is the next kernel looks like this, and then go on. So this guy is 0. This guy is like the image of this map. And now we're asking the question, what is the kernel of? So some elements outside the thing also is mapping to a 0. So there's this kernel delta n plus 1. This is cn plus 1. This is cn. This is cn minus 1. Now we're asking the question that there are two sets: kernel of delta n, this guy, this pink part, and there's this image of delta n plus 1, which is this part, which is inside. Image of delta n plus 1 is all the objects which is boundary of something else, and kernel of delta n is just every object which has no boundary. If some object is boundary of something else and has no boundary, that object has a hole inside. That's the idea. So what we do is just get the quotient and define hn of x to be this guy. That's how you. So whenever you have a chain complex, we can define a h by quotient, obviously. And this is a very general idea. You see a chain complex like this. It might be, the arrows might be reversed or something. D might take you to a higher, not k to k plus 1, not k minus 1, but k plus 1. But still, we can define the kernel quotient image at the nth nth element like this, and we can compute this is homology, this is simplicial homology, and we can compute the simplicial homology groups. This is functorial. This we can have a gluing together of objects, product of objects. How to calculate for them? We have theorems for that, and that is the second part of a first semester course on algebraic topology. The idea is more general. What we are doing is this hn would be a functor from topological space to abelian groups, right? Like we are taking, this is the hn. So hn would take a abelian group and map it to the hn of x, and it's functorial also. Okay, take a continuous map from x to y, there would be a group homomorphism from hn of x to hn of y. But let's make it way more general. Let's picture it like this. There is topological space, there's abelian group, and now define chains of abelian groups themselves. Chains of abelian groups. And given a chain of abelian groups, we can always define Hn, and this is just a CH operator. So this is a generalization. Take any kind of chain complex you can define, and maybe you can't define a chain complex. Maybe you can define something that is category theoretic, like natural transforming, like transforming over to like a chain complex or something like that. um, this chain complex is like that thing. You have a sequence of groups, and then we have a D operation, and then using that we can define the abelian groups. We can do the same thing for vector spaces. It's the idea is more general. I'm not giving you all the details here, but what I know about this is the the study of this thing, this functors from chain complexes to the chain complexes of objects to something else, like ch of some object to the object itself. That's homological algebra. That's homological algebra studies, and that is that's everything I know about homological algebra actually. And we just compose the two functors over there, and then uh, it gives out over here. I will show you some computations, not some computations, but okay. Hn of disjoint union of some topological spaces is the direct sum of the groups, and Hn of a point topological space is a sum of vector to integers if n equals 0, because there is no group over there, and there has to be a there is nothing anywhere adding sequences, so just they're getting integers with one generator. How does that work? Oh, you're inputting one point is still there. You are inputting the one dot for a triangle into there, and that is one generator, so it will produce integers, I think, and rest of them will be 0. So it's very nice and all that. So I don't know what exactly goes with cohomology, but let's just say I directly jump into subsets of Rn or whatever. The idea is more general. I would talk about manifolds only. Take a manifold, take a smooth manifold, and we can define differential forms over there. It's similar looking, not very similar looking, but the vibe is the same as Rn, subsets of Rn. Let's say U is a subset of Rn or a subset of M. It doesn't really matter. And then what you have is the differential forms. So we have omega 0 of U mapped to D0 operation, so it maps to 0 or something. We just attach it over there to make it look nice. The 1 forms, and the 2 forms, and so on. And then it ends with omega n. The dimension is the n-dimensional manifold of U, and then it stops. Everything is 0. So we define differential forms in such a way that the rest of them are 0. It's not undefined, it's exactly equal to 0 and plays nicely. So, and we know that composing these operations dn plus 1 is exactly equal to 0. So again we have a map of this form that take the 0 forms and it maps to some image inside the 1 forms, and then doing it again goes to 0, but the kernel the kernel of this map might be something else, might be larger. So, and here it's like it goes in opposite direction. The D takes from n to n plus 1. So now we define the Rham's cohomology group Hn of dr as in the same manner, exactly the same manner. But the numbers change because the D operation is going opposite. Kernel of Dn quotient with image of Dn minus 1. So this gives a group for every subset, every open subset of Rn, or every open subset of a manifold. Now, again, what we are doing very high dimensional stuff here. We are doing in the levels of sets of differential forms. What this actually means is what we are doing, we are taking the forms which are D of something else. No, we are taking the forms which are whose D is 0, which are closed forms, and then we are saying that any two closed forms are equivalent if they are separated by an exact form. So that's the quotient doing. The quotient is quotienting on anything which is whose D is 0. What are we exactly doing? So we are quotienting out anything whose. So we're quotienting out anything which is D of something else. So we don't care about the exact forms, sort of, but we actually care about them. We are asking the question, if we know that it is in the kernel of Dn, so it's D of that is 0, then we are trying to ask the question, is it in the image of Dn minus 1? Then if we quotient it, and the quotient set, quotient group has only one element, then we know there is only one equivalence class of such exact differential form. If there is no element, if the group is just the trivial group, I'm sorry, if there is only true elements, then we know there is only one. But if there is the 0 in the group is always there. So if the group is trivial, if the vector space is, these are all vector spaces actually here. If the vector space is trivial, then we know all closed forms are exact. So when does it happen? When does closed forms equal exact? Okay. So Poincare lemma has a lot of variations actually, but the main idea is simple. The main idea behind Poincare lemma is this: that when you do smooth manifold theory, and then you define this for any open set of a smooth manifold, and then you compute the groups for a few open set, few space-specific manifolds. For example, the zeroth cohomology group for a connected smooth manifold would have to be isomorphic to R, because any function whose D of f is 0 has to be constant. So we just have all constant functions. But then the constant has to be chosen to be a real number only. So it's all the real numbers. So the group is just R. For a point manifold, we see that the group is like the rest of the groups are 0. So any connected manifold will have the 0th group as real numbers. But any connected manifold will have the 0th group, the R, and the rest of the groups will be 0, because there is no differential K forms, because it's just a point manifold, and with the definition of a manifold is extended to define a point manifold. But anyways, Um, and the famous Poincare lemma comes from the idea that this HR is actually homotopy invariant. It's not just diffeomorphism invariant. If there is a diffeomorphism between two smooth manifolds, the groups are isomorphic. It is more specifically homotopy invariant. Um, if there is a smooth map that is if there is a continuous map f from x to y and then g from the reverse direction whose composition in the two directions are homotopy equivalent to the identity, it's called a homotopy. The two spaces are homotopy equivalent and it's more general than a homeomorphism. And this group is invariant another homotopy invariance. So because any contractible set is by definition a contractible set is homotopy invariant to a point, so you can contract the whole thing to a point. Because the group is same as the point, the groups is same as the point, the r and 0 for k is equal to 0 and k greater than 0. So this gives us the idea that the Poincare, the Rham's cohomology groups are really firstly about the homotopy invariance gives you an idea that it's really invariant on a topology. I give you a topology. It's not even invariant on a topology. It's more invariant under general circumstances. It's just not homotopy invariant either. It's not just homeomorphism invariant. It's just homotopy invariant. So it's like, and all the homology groups and fundamental groups are also homotopy invariant. So what we are trying to what we have observed is this object we defined using the smooth structure, using derivatives and partial derivatives in Rn, that actually should purely depend on the topology. It shouldn't depend on anything else, and that's actually the case. So you have the cohomology group, which is defined as, let's say, this is cohomology. So I defined, maybe I made a mistake here. The homology groups are defined using lower index. Yes, I have done it correctly. Hn is the homology groups, and I define, so I use Hn m of r is a homology group. It's actually a vector space now. It doesn't really matter. Now what we're taking is the dual of this vector space. It's just a dual. So we have a and this group is isomorphic to the nth Rham cohomology group. That is defined using smooth structure. So this is smoothness, this is analysis of differential forms, closed and exact structure only, and this is purely topology, and the groups are isomorphic. So this is a fundamental statement about the nature of the differential forms and the close and exactness of the properties of that. And this is called Rham's theorem. This can be proven in multiple ways. The way that it is you can define an isomorphism is this: you can integrate differential forms over chains, over this triangle that we are mapping here. So now define this map which takes a C, a class of C, and then takes a class of omega, and then maps it to this real number. So what we are defining is a function from this homology and the Hn to R, so that, and this gives you isomorphism between these two, a dual of the homology to cohomology and the Rham's cohomology. This is one way to do it. There are other ways to do this, and that relies, which I'm going into this week and the weeks afterwards, is coming. The idea is coming from Poincare lemma. Poincare lemma is saying that given a smooth manifold, every differential form is exact in some small neighborhood, in some small open set, then if it's really exact in a small open set, then it's exact in almost all the places. Then why don't we have a global differential form which is d of something else? So here we have a fi such that it's f d of fi is omega. यहाँ पे we have a dfj which is omega. So why don't this fifj give you a global form? Because they don't, the intersection don't happen nicely. The crazy thing happens at the intersections, and that idea is that gluability of this differential forms, its f's, that gluing them together is not possible, or is it possible? That is what the topology is giving you. That is what that is why it depends on the topology only. It's just the gluing, that's it. And gluing means what's the local global, I said glue it together, can be gluable. And we use sheaves. Sheaves is a kind of local global object. It's a category which you define, and the proof of de Rham's theorem using sheaves is what I'm getting into. It's a sheaf theoretic proof. This is the major idea, that the Poincare lemma and the de Rham's theorem are the two major theorems there. There are multiple ways to look at it. This isomorphism and the Poincare lemma sheaf theoretic isomorphism theorems, both in least smooth manifolds. The first one is given, the second one is harder, at least to me for now. I don't know much about it yet. This is stuff. This is the whole theory of the idea. Now let's do some computations. I don't know the computations that well. I've not computed them myself. But what we can do is, I'll give you one example without some very nice proofs or something like that. Let's say this is the punctured plane R2 minus 0. This is connected, so H0 is trivial. Of DRAM. You don't need to write DRAM. All the cohomology are the same. They're isomorphic. That's the fun about this whole thing. But we're computing the DRAM, so let's write it. What is H1 of DR? We need to figure out all the one forms which are non-conservative in the following sense, that any one form is conservative if integrating over closed loops. Integrating over closed loops give you 0 for all C. Then omega is conservative. We will see this is if and only if you have two paths and they give you the same answer. Two paths with same endpoints. Gamma 1 omega is same as gamma 2 of omega. I'm not giving any proofs here. Now we notice that there is another isomorphism. This is if and only if omega is equal to d of f. So conservativeness is exactly equal to the exactness. Now we just have to figure out if there is a non-conservative one form in R2 minus 0, and there is one. The differential form, which is written conventionally as this. Notice that this is not defined at 0, 0. Um, this is not d of anything in the whole domain of R2 minus the origin. But there is a theta. We can define a theta as tan inverse y by x, right? But tan inverse y by x is not defined in all over the angles. If let's say we are only taking the upper half plane, then the theta is defined, then it's exact. This is a contractible domain. All the one forms are all the one form closed one forms are exact. But if we take the whole domain, then this there is no d theta, because integrate this d theta over a closed loop here that contains the origin, it will be 2 pi. And it has to be 0 if it's conservative, so it's not exact, not conservative. And we can show that there is only one equivalence class. So this h1 of the punctured plane is actually spanned by this d theta. So we're taking equivalence classes. Anything that you can add any exact forms and that would still not matter, because that's just equivalence class. We're quotienting it, quotienting the group in the cohomology group, so that's why there's equivalence classes here. And we can also show that h2 of x is 0. So if there is some f whose divergence is 0, then whose domain is a punctured plane, and there exists g such that f is curl of g. So this gives you a nice example of why electric field and magnetic field are so different. At least in the plane, in R3 things go differently. It's an exactly opposite thing happens. If you have in R3 exactly opposite thing happens. Something the h1 is 0 but the h2 is not 0. So that's why if you keep electric field, curl of electric field, let's say it's not 0 here, so you remove this point from the domain and take the rest of the plane as your domain, then what will happen? There will be no potential which is defined in all over the plane, in all over this plane. So you keep a resistor here and a resistor here, and attach potentiometers here, voltage meters, voltmeters, voltmeters here, and voltmeter here, v1, v2. They will show different values because the paths taken by two of them is different. They're measuring two different things. Now, how exactly the physics goes on, if you remove one from the other continuously, what will happen? I don't know. I would imagine you can't do that in R2, but okay. In R3 you can do this, and that's why. And that's purely so, because if the non-conservative part is here and you were doing the experiment here, it won't matter because you remove this part and then take this domain. This is fine to work. But there is a potential. So I would give you two more theorems. If your space is simply connected and pi 0, I mean this path connected and simply connected, then this implies actually is just simply connected, right? Hn of u is simply connected is, sorry, h1 of u is 0, and this condition is not the reverse of this is not true. Your h1 might be 0 but it might not simply connected. And that's why the homology and cohomology, homology, and um, fundamental groups are not the same. They are not at all the same. So that's why this theorem is written in multiple calculus books. If your domain is simply connected, then your if the curl is zero, then then the vector field is gradient to something else. And this is one theorem you can prove. You just use that conservativeness property that's given in Lie. Now, what I also wanna show is the Rn version of Poincare lemma. Okay. Okay, let's take this domain. I don't know. A domain is star shaped. A convex domain is where every point between every line, the line containing between 2 points is contained in the domain. So this is not exactly convex. It's going outside. Convex has to be like this. It has to contain all the points. A more general version is this. Our domain is star shaped with respect to a center X. If you take any point and there is a line contained between that, and the line between the 2 points in Rn is contained in the set. That's called a star shaped domain in Rn. You can define this in any vector space. And what will happen is you can define a contraction. Take this point slowly here, so you can define a homotopy from the whole set to the point, this point exactly. And that's why a Poincare lemma equivalent statement is this: any contractible domain in Rn has HNs all to be the null groups for n greater than 0. And you can show that without using anything more than definition of this thing. So we just define a integral, and that's it. We can define the integral because we have a line between any 2 points. We also could have done it if the loops are contractible, but only for the only for n equals to 1, the 1 forms. That's why simply connectedness, because you can contact all the loops, that's why the h1 is 0. Yeah. But if you have a star shaped domain, you can do it for all the forms. And I haven't proved this yet properly. I have proved it for, like, this is really easy to prove for 1 forms and 2 forms using curl and stuff. Other stuff is also the same. It's given over here. That's the major idea. Yeah. So that's it.